You've shipped a fast Swift app that's actually paying a tax on every single method call, and you don't even know where. And somewhere in that same codebase, you probably have a struct that looks like a value type, behaves like 190% of the time, and is silently sharing mutable state through a class property you forgot about. If you can't explain static versus dynamic dispatch in an interview, you get cut. Not because it's trivia, because it tells the interviewer whether you understand what the compiler is doing with your code, or whether you've just been writing Swift by vibes. In the next few minutes, what static and dynamic dispatch actually are, where they show up in real code you write every week, why this isn't academic, how to answer this in an interview, and exactly what happens, and what breaks, when a struct holds a class property. If you're the kind of developer who wants to know what's happening below the syntax, subscribe. This channel is for engineers building production iOS apps in 2026, not people looking for copy-paste tutorials. Part 1. What dispatch actually is. Dispatch is how the program decides which piece of code to run when you call a method. There are two main paths. The compiler can know the answer ahead of time, or the program can figure it out at runtime. Static dispatch means the compiler knows, at compile time, exactly which function implementation you're calling. It can inline it, optimize it, skip any lookup. Dynamic dispatch means the implementation isn't known until runtime. The program has to look it up, usually through a table. That's the whole concept. Everything else is just which Swift feature uses which one. Structs and enums, static dispatch, full stop. Value types don't support inheritance, so there's nothing to look up. The compiler always knows which method body runs. Classes are dynamically dispatched by default, because classes support inheritance, and the compiler has to allow for a subclass overriding that method. Swift implements this with a virtual method table, a vtable. Each class instance carries a pointer to a table of function pointers. Calling makeSound means look up the table, find the right pointer, jump to it. That lookup is the cost. Protocols are where most developers get it wrong. A protocol method call is dynamically dispatched through a witness table. Same idea as a Vtable, built per conforming type instead of per class hierarchy. Call makeSound on a value typed as sound making, and Swift doesn't know the concrete type at compile time. It goes through the witness table. That's dynamic dispatch, even on a struct. That last point trips people up constantly. Protocol conformance for a struct is still dynamic dispatch when called through the protocol type E. Dispatch is about the call site, not the underlying type. How do you force a class method to static dispatch? 3 ways. Final tells the compiler this can never be overridden, so it skips the Vtable entirely. Private does something similar within its scope. And calling a method directly on a concrete, non-polymorphic type A, rather than through a protocol or superclass reference, lets the compiler resolve it statically when it can prove the concrete type. This is also why generics with concrete type constraints can be statically dispatched, while existentials, any sum protocol, go through dynamic dispatch via the witness table. Same protocol, different mechanism, real performance difference. Part 2. Where you actually see this. This isn't a whiteboard concept. It shows up in 4 places you touch constantly. 1. SwiftUI view bodies. Every time you write some view, that's static dispatch in action. SwiftUI deliberately avoids protocol existentials for view composition because dynamic dispatch through a deeply nested view tree, every frame, would be measurably slower. 2. Dependency injection. Anywhere you inject a protocol-typed service into a view model for testability, a network client, a persistence layer, that's dynamic dispatch on purpose, so you can swap in a mock. 3. UITableViewCell and UICollectionViewCell subclassing. Every override func in a cell subclass goes through a vtable lookup. Not expensive in isolation, but in a cell reused hundreds of times per scroll, it's part of the cost profile. 4. Framework and SDK boundaries. Anytime you conform to codable, equatable, or a delegate protocol, and that conformance is called through the protocol type rather than the concrete type, you're paying for a witness table lookup. Invisible unless you go looking for it in instruments. If you've never opened instruments and actually looked for this, that's the gap. The concept isn't useful until you've seen it cost real milliseconds. Part 3. Why this actually matters? This isn't about shaving microseconds off a method call most of the time. It's 3 things that actually affect how you build. Performance predictability. Static dispatch lets the compiler inline, optimize, sometimes eliminate code entirely. Dynamic dispatch is a hard boundary the optimizer can't see through. On a hot path, a custom layout engine, a render loop, a parsing routine running every frame. That boundary is the difference between smooth and janky. API design. Knowing dispatch means you can make a deliberate choice between any protocol and a generic constraint, between a class hierarchy and a final class with composition. SwiftUI's entire architecture is a bet on static dispatch over dynamic. That's not incidental, that's the design philosophy. Debugging. When a call doesn't go where you expect, especially with that OBC dynamic and method swizzling, understanding dispatch is what lets you reason about what's happening instead of guessing. This is the difference between a developer who ships features and one who can explain why the architecture works the way it does. That second kind gets the senior offer. Here's the part most tutorials never cover, and it's the question that actually separates people in interviews. What happens when a struct holds a class? Because the second you do this, you don't fully have a value type anymore. It looks like one and behaves like one in some ways, but not all. If you don't know exactly where that line is, you will ship a bug that looks impossible to reproduce. Stay with me, because this is the part that actually changes how you write Swift. Let's make this concrete. Car is a struct. Copy it, and Swift copies the struct's own storage. Name gets duplicated? Fine. But engine is a reference. Copying the struct copies the pointer, not the engine instance itself. So now you have two car values, fully independent as far as the compiler's concerned, but they share the same underlying engine. Mutate horsepower through one, and the other sees the change too. That's not a bug in Swift. That's exactly what reference semantics does. It's just hiding inside something that looks like a value type. This is exactly the kind of bug that's brutal to track down, because everywhere else in your codebase, structs behave the way you expect. The one place they don't is the one place you forgot to check. What do you actually do about it? Two real options, and the right one depends on intent. If engine doesn't need reference identity, if two engines with the same horsepower really are interchangeable, make it a struct. Problem solved, full value semantics restored. If engine does need to be a class, expensive to copy, or genuinely a shared mutable resource, implement copy on write manually. Check is known uniquely referenced before mutating, and copy first if the reference is shared. This is the exact mechanism Swift's standard library uses for array, dictionary, and string under the hood. You're not doing anything exotic. You're doing what the standard library already does, on purpose, in your own type. Knowing this pattern and being able to explain it tells an interviewer you understand value semantics at the implementation level, not just the marketing pitch. Part 4. How to answer this in an interview. Now, how do you put all of this together when someone actually asks you the question? Static dispatch is resolved at compile time. Dynamic dispatch at runtime. In Swift, classes use vtables, protocols use witness tables. I use dynamic dispatch deliberately when I need polymorphism, like protocol-based mocking in tests, and I reach for final or generic constraints on hot paths where I want the compiler to inline and optimize. One thing worth knowing too, even a struct can end up with hidden reference semantics if it holds a class property, so I'm careful about that when I'm reasoning about copy behavior. That answer tells the interviewer three things at once. You know the mechanism, you know the cost, and you make the choice on purpose instead of by accident. If this helped, subscribe, drop a thumbs up, and tell me in the comments, have you ever debugged a shared mutation bug in a struct and traced it back to a class property? I want to hear how you found it. If you're building a real iOS app and need senior level guidance to scale it the right way, visit tony-trejo.com and let's talk.